Now, this is all fine and good for arithmetic sequences, but what about geometric sequences? By the way, as we do these geometric sequences, I'm going to recommend that you make sure that you have yourself a calculator handy. And in fact, I'm going to do the same. I'm going to see, there we go. I've got a calculator here on my computer. In fact, if you're on your Chromebook, you've got a calculator there too, I'm pretty sure. So I've got a calculator handy, so just making sure I have a calculator nearby that I can use because I am going to need it and be ever so grateful that I have it. I'm going to show you some cool calculator tricks today too. It's going to be awesome. Just saying. So here's the deal. We've been dealing with arithmetic sequences, so let's shift to geometric sequences for just a moment. You guys know that, I have all kinds of things here. That's what I wanted. You guys know that geometric sequences means we're multiplying and dividing, and that instead of a common difference, we now have a common ratio because we're doing that multiply thing. So, you know, I don't have issues with bugs or even bats. I don't even mind snakes. I'm cool with snakes. But I don't do spiders. I don't do spiders. That is not acceptable. Spiders and I have a deal. They can live outside to their heart's content, but they can't come inside because if they come inside, death will be waiting for them. That's my deal. So when it comes to bugs, bats, spiders, and any other creepy crawlers, finding one spider in my house is finding one too many, okay? Not cool. But typically when it comes to cells, the more the better, right? Usually. Animals, plants, fungi, slime, mold, all these other living creatures, all living creatures are composed of what we call eukaryotic cells. I am not your biology teacher, so you'll have to ask them for more detail on that. But basically how it works is this. During growth, there is generally a cell that they call the mother cell. And then the mother cell divides itself into two daughter cells. So you start off with one, but of course it splits in two because that's what cells do. And then of course each of those two cells, those two daughter cells, then divide into two more cells and so on and so on and so on. So you can see what's happening here. So if I were to show you the sequence that represents growth of eukaryotic cells, that means that I started with one cell, which split in two and split in two and split in two and split in two. So I had one, but then I had two, but those became, I doubled that, which became 4, doubled that, which became 8, doubled that, which became 16. So what I'd like you to do first for part A, can you just describe why this sequence is geometric and identify for us the common ratio? Go ahead and hit pause, jot that down, hit play to keep going. So this sequence is geometric because it's being multiplied by a constant every time, right? So the sequence is geometric because it's a constant that's being multiplied to produce the next term. And of course, we can see that our common ratio, oh, sorry for the typo. I can fix it. Maybe I can fix it. I can fix it. It's not a ration, it's a ratio. There, that's better. The common ratio is 2. Now, I do want to point something out here real quick. Notice that for that first cell, no divisions have taken place. So we have a table here for part B. We have a lovely table. And so for 0 cell divisions, nothing is split yet. I've only got, this is term number 1. That means I've only got one little cell in here. So go ahead and keep going. Fill in all of the table here. Term numbers. So this is after split. Fill in your term number. Fill in the total number of cells. If you need a calculator to help you out, it's cool. I got it. So hit pause to fill in your table. Hit play when you're ready to keep going. All right, so after one division, that actually gives us the second term, which is 2 cells. 2 divisions gives us the third term, which we'll notice is 4 cells. and so on and so forth. So after 3 divisions, I'm on term number 4 with 8 cells, term 5 with 16, term 6 with 32, term 7 with 64 cells, term 8 with 128 cells, term 9 with 256 cells, and term 10, which gives me 512 cells. So again, notice that just like with our baseball home run hits, notice that the number of divisions is off by 1 from our term number because the initial term was from before anything split. All right, so our number of cell divisions is always 1 less than our term number. And of course, our actual term value, our total number of cells, just keeps doubling, right? That's what keeps happening here. So my question is this: if I cut it off here and I just ended up at the 9th term, how would you calculate the 10th term based on the 9th term? Hit pause, write it down, hit play when you're ready to check. So of course, if I had the 9th term and I wanted the 10th term, I would just multiply the 9th term by 2, right? Right. And of course, this takes us to the recursive formula for geometric sequence. Now, it's a little different than our arithmetic formula. Our arithmetic formula was adding our common difference, right? Because it was arithmetic. But this is geometric, where we're multiplying our common ratio. That's what makes it geometric, is multiplication. So if I want to find the nth term, I need to find the term right before it, g sub n minus 1, and multiply it by my common ratio. Fair enough. If I want the 10th term, I need to use the 9th term and multiply it by whatever the common ratio is, whatever that pattern is that's going on. No big deal. Notice we're using G's now instead of A's. Of course we are. It's geometric. Yeah. So let me give you an idea, a little worked example here of what we're talking about. So let's consider this lovely sequence that I have here, 4, 12, 36, 108. And let's say I wanted to find the 5th term. So here's our formula that we use. So if I want the 5th term, then everywhere I see an n, I'm going to plug in a 5. So I did. Remember that r is our common ratio, and it looks like we're times 3 times 3 times 3. We're multiplying by 3, so my common ratio is 3. So fine, if I want to find g sub 5, the 5th term, I need to find g sub 4. 5 minus 1 is 4, times that by 3, and I should be good to go. I can see my 4th term is 108, so I grab a calculator, and I have 108 times 3, and that tells me that my 5th term is going to be 324. So recursive formula, super easy, right? I just need the term right before it, multiply it by my common ratio, and boom, I got my next term. That's right. That's how that goes. So here's what I would like you to do. I would like you to write a recursive formula for this sequence. So we've already gone pretty far on this. I would like you to write a recursive formula for the sequence and use the formula to determine the 12th term in the sequence. And then, of course, explain what your answer means in terms of our cell division problem. So go ahead and hit pause to work that out. Hit play when you're ready to check your work. So I'm busting out the recursive formula. Yeah, I did. I'm looking for the 12th term, so everywhere I see an n, I'm going to plug into 12. On this case, it looks like it was times 2 times 2 times 2 times 2 all the way down, so I'm going to say that my r, my common ratio, is 2. Yay! So if I want to find the 12th term, that means I need the 11th term to multiply it by 2. Now, I finished off at the 10th term, but if I multiplied that by 2, that tells me my 11th term would be 1024. And of course, for my 12th term, I will multiply by 2 and be grateful I have a calculator. And I will get 2048 and say, thank you, Mr. Calculator. Ding, it's all good. We need to explain what this means. So if it's the 12th term, that means there's only been 11 divisions of the cell. So that means there'll be a total of 2,048 cells after 11 divisions. Now, of course, this was all fine and good because we were only looking for the 12th term, which was pretty easy to do since we'd finished off at the 10th term. The problem, as you know, comes is what if I'm looking for term number 22? Like suddenly I don't want to make that table anymore. It's not fun. So this is where we go to our explicit formula. So much better when you start getting really, really, really far down the terms in your sequence. And it looks like this. So the explicit formula to determine the nth term of a geometric sequence looks like this lovely guy right here. So of course, this is my nth term, g sub n, whichever n that is that I want. And just like with arithmetic, I do need my first term. So g sub 1, you are going to want your first term. Also similar to arithmetic, you are going to want that common ratio, r, right? We knew that was going to come back. Notice it's being multiplied, but r now has an exponent. Did you catch this? So instead of just times r, I now have times r to the n minus 1 power. This is a new trick, isn't it? This is a new trick. So I'm going to show you how this works. I have a worked example for you. Of course I have a worked example for you. Of course I do. So you can use the explicit formula to determine the 20th term in this problem situation. So I'm like, dude, 20 terms? Holy crud. Hang on a sec. I'm getting a call. Why am I getting a call? I'm back. Did you miss me? No, because it was only a split second. So you didn't even notice I was gone. All right. So here we are. We've got a worked example of our explicit formula to help us determine the 20th term in this situation. So here is my formula. G sub n equals g sub 1 times r to the n minus 1. Since it's the 20th term, everywhere I see an n, I'm going to plug in a 20. For our particular situation with our cell division, we start off with one cell. So our first term is 1. So instead of g sub 1, I'll plug in a 1. It's doubling, right? It's multiplying by 2 every time. So my common ratio r becomes 2. Now, here's a few important tricks. So the deal is, the first part's easy. You need to make sure you take care of your exponents first, right? So 20 minus 1 is 19. Now, I'm going to show you something. Did you know that your calculator can do any exponent you want it to? Check this mess out. Watch this. I can do 2 to the 19th power. Now, my calculator, because I'm using the calculator on Google, has a button that says x to the y power. Your button might look different. It might look like, so instead of x to the y power, so instead of x to the y power, your button might look like y to the x power. Or if you have like one of those nicer TI calculators, it looks like what we call a caret. So it's just like a little like dook. It looks like this right here. So if you hit this button, it will let you type in an exponent. And so I can now type in 2. If I hit the button, I can now type in 2 to the 19th power, and I can hit equals, and it found it for me. So this is a super cool button to know about, this exponent button, whichever one that it looks like on your calculator, but it allows you to do any exponent you want. So I can do 2 to the 19th power. So I would hit, again, I'll show it one more time. I can hit 2, hit my magic exponent button, and then 19. So I hit my base, magic exponent button, and then my exponent. And I hit equals, and boom, there it is. Yeah, love that button. So 2 to the 19th power gives me 524,288. Of course, my final step then with my PEMDAS is to multiply by 1, which gives me 524,288. So the 20th term of the sequence means that after 19 cell divisions, there are a total of 524,288 cells. That's a lot of cells. It's a lot of cells. So you can see it gets really, really big, really fast. These geometric sequences, because we're multiplying, they get big fast. They get big fast. So now that you know how this works and we know our pattern of our cell divisions, I would like you over on page 139 to use your explicit formula to do number 3, all 4 parts, A, B, C, and D, to help you find the number of cells for each number of divisions. Remember that the number of divisions is off just by 1 from the term that you're looking for, so double check that first. So go ahead and hit pause, work out number 3, A through D, and then hit play when you're ready to check your work. All right, so 11 divisions means that I'm on the 12th term. So when I look at my formula, everywhere I see an N, I'm going to plug in a 12. I'm going to plug in a 1 for my G sub 1 because that's my first term. And I'm going to plug in a 2 for my R because that's my common ratio. I am going to grab a calculator. So 12 minus 1 is 11. Grab my calculator to do 2 to the 11th power, which gives me 2,048, which if I times by 1 is 2,048. For 14 divisions, that means I'm looking for the 15th term. So everywhere I see N, I'm going to plug in a 15. So this is going to be G sub 15, and this is going to be 15 minus 1, also known as 14. And of course, my first term is 1. My common ratio is 2. 2 to the 14th power. Thank you, Mr. Calculator. Because remember, we do have to do exponents before we multiply. So 2 to the 14th power is 16,384. And it's still that because I'm multiplying by 1. Yay! 18 divisions means I'm looking at the 19th term. So again, everywhere you see an N, I'm going to plug in a 19. My first term is still 1. My common ratio is still 2. 2 to the 18th power is 262,144 times 1 is still 262,144. And last but not least, 22 divisions means I'm looking at the 23rd term. So that means everywhere you see an N, I'm going to plug in a 23. My first term is 1. My common ratio is 2. I will grab a calculator because 23 minus 1 is 22. 2 to the 22nd power. 4,194,304 times 1. I can handle that part. So after 22 divisions, I have 4,194,304 cells. That's a lot of cells. We're going to change it up on you just the tiniest little bit, just the tiniest little bit. Change it just a little bit. Let's say instead of starting with 1 cell, I start with 5. And let's say that each cell, instead of dividing into 2, divides into 3. This changes things. So to get us started, I would like you to write the first 5 terms of this sequence, if we could find a cool cell that would do that. And then, so hit pause, give me the first 5 terms of your sequence, and then hit play when you're ready to check your work. So I'm writing the first 5 terms of the sequence. Yeah, I start off with 5 times 3 gives me 15, times 3 gives me 45, times 3 gives me 135, times 3 gives me 405. So this is different than what we did earlier, isn't it? My G sub 1, my first term is now 5, and my common ratio R is now 3. So it's changed as we go to use our formula, our explicit formula for question number 5. So now that you have this new sequence, this new pattern, this new way of looking at it, I would like you to determine the total number of cells in the Petri dish for each number of divisions. If instead we're starting with 5 and we now have a common ratio of 3, how's that going to change? What's that going to look like? Go ahead and hit pause to do A and B, and then hit play when you're ready to check your work. All right, please don't forget 13 divisions means I'm looking for the 14th term. Oh, because remember that original term, 5, nothing had been divided yet. So 13 divisions means it's the 14th term. So everywhere I see n, I'm going to plug in a 14. My g sub 1 is now 5, and my r is now 3. 14 minus 1 is, of course, 13, and I grabbed a calculator. Please grab a calculator. Please remember PEMDAS means that you need to do your exponents before you multiply. Exponents first. So 3 to the 13th power, according to my lovely calculator, is 1,594,323. Now I can multiply that by 5. And it turns out after 13 cell divisions, I have 7,971,615 cells. That's a lot of cells. 16 divisions means I'm going to be looking at the 17th term. So everywhere I see an n, I'm going to plug in a 17. So that's going to be g sub 17. That's going to be r to the 16th power because 17 minus 1. My first term, g sub 1, is now 5. My common ratio r is now 3. I grabbed a calculator. Remember exponents first. So 3 to the 16th power gave me 43,046,721 times 5 gives me, it means that after 16 divisions, there are 215,233,605 cells. I hope you got a really big Petri dish to fit all this in. That's a lot. That's a lot of cells. Just saying. One last little thing we're going to do before we go. So you know how in the last lesson you had those graphic organizers and you glued in the sequences and you glued in the graphs, and underneath them it said that they were looking for a recursive formula and an explicit formula? That's what you're going to do. So you're going to go back to those graphic organizers on pages M1-117 to M1-127. You've already done the top part. Now you're going to do the bottom part. So you already did the sequences with the graphs. Now you're going to give me the formulas to go with them. So pay attention to whether it's arithmetic or geometric because that makes a difference. So I'll show you what I mean. So I'm going to go back to my organizers. Here they are. My first sequence is sequence B. Maybe your first sequence is a different one. Mine is B. And we said that the pattern was that we're adding 2 and it started with a -4, all that good stuff. So if I'm looking for the recursive formula, then that's our a sub n equals a sub n minus 1 plus d. So fine, for my d, I'm just going to plug in a 2. And here is my recursive formula. For the explicit arithmetic formula, if you recall, that was a sub n equals a sub 1 plus d times n minus 1. I know what d is. D is 2. I know what my first term is. My first term was a -4, so I just plonk that in there. Boom, there's my explicit formula, and that's all you need to do. So go ahead and do the rest of your arithmetic sequences, and then, so hit pause to do the rest of your arithmetic sequences, just like we did this first one, and then hit play when you're ready to check your work and move on to the geometric ones. So for my next sequence, I have E as my next sequence. I can see that my common difference is a -9/4, so that's what I put into my recursive formula. I can see that not only is my common difference -9/4, but that my first term is 4, so those are what I put into my explicit formula. For my next sequence H, I can see that my common difference is 4, so I put that, +4, so I put that into my recursive formula. I can see that my common difference is 4, and my first term is -20, so I put that into my explicit formula. My next sequence is K. I saw that my common difference was a -1.5 because we were subtracting. So I put that into my recursive formula. And then not only is my common difference negative 1.5, but my first term was 6.5, so I put that into my explicit arithmetic formula. And my last arithmetic sequence, sequence n, I can see that my common difference is negative 20.5, so I put that into my recursive formula. And I can see not only is my common difference negative 20.5, but that my first term is 1,473.2. So I put that into my explicit formula. And I wrote kind of too big. I probably should have written smaller so it would fit better. Sorry, that's how it goes. Ready for the geometric ones? And again, I'll give you a head start with the geometric ones. I'll help you out with the first one, and then I'll set you free on the others. So I noticed that my common ratio is 2. So for my geometric formula, my G sub n equals G sub n minus 1 times R. All I did was I substituted for R. I'm just plugging in that common ratio of a 2. Yay! For my explicit formula, I have G sub n equals G sub 1 times R to the n minus 1. I already know that R is 2. And if I look at my sequence, I can see that the first term is 45. So I put that in there for G sub 1. So you're going to keep doing this for all of the rest of your geometric sequences. Go ahead and hit pause to work your way through them, and then hit play when you're ready to check your work. So if we keep going, I can see my common ratio for sequence C is 3. So for my recursive formula, I just plugged in a 3 for my R. I can also see that my first term is a negative 2. So for my explicit formula, I plugged in a negative 2 for my G sub 1, and I still plugged in a 3 for my common ratio R. I have sequence F next. For sequence F, my common ratio was 0.1, so I just plugged that into my recursive formula. And then I also see that my first term is 1,234, so I put both my first term and my common ratio R into my explicit formula. For sequence J, I can see that my common ratio R is 1/2. So I plugged that into my recursive formula. And I did put parentheses around it just to protect it, keep it safe. And that means for my explicit formula, not only do I need my R equals 1/2, I also need my first term, which is -5. So I plugged in what I had. Boom, there you go. My next sequence is sequence M, which means my common ratio is a -1/4, which I put into my recursive formula. Notice I included the negative inside those parentheses. You don't want to lose it. So I deliberately use parentheses to keep that negative safe and the fraction safe. But for my explicit formula, I also need my first term, which is -16. And I plugged in both for G sub 1 and for R. Next up, I have sequence P, where my common ratio is a -3. So I put that into my recursive formula. So times R. Again, I use parentheses to help keep the negatives safe and tucked in where he belongs. Otherwise, they get lost. Negatives tend to run away. You got to hang on to those guys. And of course, for my explicit formula, not only do I need my R, I also need my first term, which in this case is a -4. So I'm going to plug both of those in for my first term and for my R. All right, guys. As always, I hope you found this helpful, and I hope you found this useful. You got questions or concerns, feel free to ask me during class, pop in during office hours, or of course, you can always email me. And I'll see you soon. Bye.